Hello everyone, hope you're fine. In this video, we're gonna use Python to simulate random sampling. We know that we use sample data to make point estimates about population parameters. So if our sample size is large enough, our sample mean will give us a pretty good estimate of our population mean. And we continue the same scenario from previous video. If you didn't watch it, I recommend you go back and check it. It's a video labeled with normal distributions in Python. So we're analyzing data on the literacy rate for each district of a country. But here there is a small difference. Imagine that we are in a stage that we are asked to collect the data on district literacy rate, and we have limited time to do so. We can only survey 50 randomly chosen districts instead of 634 districts included in our original data set. So here the goal of our research study is to estimate the mean literacy rate for all 634 districts based on our sample of 50 districts. To start, we import the Python packages we will use, including NumPy, Pandas, and statsmodels.api, and the library matplotlib.pyplot. As always, we rename each packaging library with an abbreviation NP, PD, PLT, and SM. Also, to load the SciPy stats model, we write from SciPy import stats. So, first, we'll want to get a random sample of 50 districts. And a cool feature of Python is that we can use code to simulate random sampling and choose the desired sample size. To do this, we use the sample function, which is in Pandas. To simulate random sampling, we use the following arguments in the sample function: n, replace, and random underscore state. N refers to the desired sample size. Replace indicates whether we are sampling with or without replacement. And random underscore state refers to the seed of the random number. So for this example, we set the sample size to 50, which is 50 district literacy rates from the overall literacy column. And the second argument is replacement. But let's first see what is replacement. So when a population element can be selected more than one time, we are sampling with replacement. But when a population element can be selected only one time, we say that we're sampling without replacement. And here, for the purpose of our example, we will sample with replacement. And finally, the final part of the code is random underscore state, or the seed of the random number. A random seed is a starting point for generating random numbers. So we can use any arbitrary number to fix the random seed and give the random number generator a starting point. So now we're good to go. First, we name a new variable, sampled underscore data. Then we set the arguments for the sample function. And sample size equals 50, replace equals true, because we're sampling with replacement. And for random underscore state, we choose an arbitrary number for our random seed, for example, 31,208. And we write the name of the variable, sampled underscore data, to display it, and click on run. So the output shows 50 districts selected randomly from our data set, and each of them has a different literacy rate. And now we have our random sample, so we use the mean function to compute the sample mean. First, we name a new variable, estimate1, and next we use the mean function to compute the mean for our sample data. So then we click on run. The sample mean for district literacy rate is about 74.22%. This is a point estimate of the population mean based on our random sample of 50 districts. We know that due to sampling variability, the sample mean is usually not exactly the same as the population mean. So now let's see what will happen if we compute the sample mean based on another random sample of 50 districts. To generate another random sample, we name a new variable, estimate2. Then we set the argument for the sample function. Once again, n is 50, replaces true. But this time, we choose a different number for our random state to generate different sample from the previous one. Let's say 56,810. And finally, we add the mean function at the end of our line of code to compute the sample mean. And click on run. So for our second estimate, the sample mean for our district literacy rate is about 74.24%. Due to sampling variability, this sample mean is different from the sample mean of our previous estimate, 74.22%. But we can say that they are really close. From the central limit theorem, we know that when the sample size is large enough, the sample mean approaches a normal distribution, and as we sample more observations from a population, the sample mean gets closer to the population mean. So the larger our sample size, the more accurate our estimate of the population mean is likely to be. For this example, the population mean is the overall literacy rate for all districts in the nation. And from previous video, we know that the population mean literacy rate is 73.39%. And we can see that both these estimated sample means of 74.22% and 74.24% are relatively close to the population mean. So now imagine we repeated this study 10,000 times and obtain 10,000 point estimate of the mean. Meaning that we take 10,000 random samples of 50 districts and compute the mean for each sample. We want to code this in Python. First, we need to create an empty list to store the sample mean for each sample, and we name it estimate_list. Second, we set up a loop with the range function, which the loop will run 10,000 times and iterate over each number in the sequence. And third, we specify what we want to do in each iteration of the loop. Like the sample function tells the computer to take a random sample of 50 districts with replacement, and the argument n equals 50 and the argument replace equals true. So as we all know, the append function adds a single item to an existing list, and in this case, it appends the value of the sample mean to each item in the list. So next, we create a new data frame for our list of 10,000 estimates. We name this new variable estimate_df to store our data frame. And now we name a new variable mean_sample_means, which computes the mean for our sampling distribution of 10,000 random samples. And then we display the value of our variable. So as you can see, the mean of our sampling distribution is about 73.41%. And as you know, this is essentially identical to the population mean of our completed data set, which was about 73.4%. So we're good to go now, and we want to visualize the relationship between our sampling distribution of 10,000 estimates and the normal distribution. to do so, we plot both of them at the same time. So we have written the code for this and we'll run it. And we have the graph. So we can have 3 takeaways from this graph. First, as the central limit theorem predicts, the histogram of the sampling distribution is well approximated by the normal distribution. As you can see, the outline of the histogram closely follows the normal curve. And secondly, the mean of the sampling distribution, the blue dotted line, overlaps with the population mean, the green solid line. This means that the 2 means are essentially equal to each other. And thirdly, the sample mean of our first estimate of 50 districts, the red dashed line, is farther away from the center. This is due to sampling variability. So the central limit theorem shows that as we increase the sample size, our estimate becomes more accurate. So we conclude that for a large enough sample, the sample mean closely follows a normal distribution. And that's it. Thank you so much for watching this video. I hope you liked it. And if you did, please like it and subscribe to my channel. I'll see you in the next videos.